So let's start with a fairly artificial example. Right? This is designed purely to run through the algebra to make sure we understand what the definition is saying. So let us start with a sample space of 10 elements. Let's call them 1, 2, 3, 4, up to 10. If you wish, we can think of this as an experiment where we throw a 10-sided die with the numbers 1 through 10 inscribed on the faces. Naturally enough, for this simple stylized experiment, I will assume that this 10-sided die has no bias towards any face. In other words, we are randomly selecting an element from 1 through 10, or in still other words, the mass function associated with the probability measure for this problem is uniform. It puts equal mass of 1 in 10 on each of the 10 faces. We've taken another liberty with notation, and we've done this again in the past. To specify the probability measure in these simple finite cases, as we know, all we require is the mass function, which gives us the atomic probabilities for every singleton set. Formally, we should say, here is a singleton set, the element I. And then that is a set. The probability, naturally enough, we put round brackets around that set. That's how we define probability measure. The probability measure is a set function which takes a set as an argument. But this unnecessarily complicates our notation. Now we have brackets, curly and round, floating all over the place. Where there's no chance of ambiguity, we'll simply drop the round brackets. And we'll say the probability measure P of the set which arises in the curly brackets following it, in this case a singleton set I, is 1 in 10. Now we've got the sample space, we've got the probability measure. To compute generic probabilities, we simply appeal to additivity and simply sum atomic probabilities. What are the events of interest? Well, let's put together just this grab bag of events. There's nothing particularly insightful about the way I've constructed these events. They are just sets. The target event A is a set comprised of the elements 2, 3, 4, 5, and 6. And I've given you 3 other possible events which could serve as ancillary events for the purpose of communicating side information about what the experiment actually happened. So I've given you 3 more events, B, C, and D, with various subsets, as I've given you there. And your problem now is to evaluate the conditional probabilities of A, given that B has occurred, A, given that C has occurred, A, given that D has occurred. And finally, A, given a composite event, B intersection C has occurred. Pause the lecture and work your way through this to allow you to settle concepts before you turn to the next slide and to the answers. All right, now that you're back, let's verify what you've got. We should begin by writing down the various events of interest and their probabilities. So let's start with the sample space. The sample space omega is comprised of the universal set of the integers 1 through 10. Normalization of probability measure tells us that this entire set is certain. It has got probability 1. The target event A is comprised of the elements 2 through 6. It has 5 elements. We're dealing with a combinatorial setting. Therefore, the chance of A by additivity is 5 in 10 or 1 in 2. B, C, D, and B intersection C are the ancillary events of interest to us, which are casting side information upon the problem at hand. Each of these events now can be identified with a particular subset, and each of these subsets then will give rise to a particular probability, 6 in 10 for B, 5 in 10 for C, 4 in 10 for D, and B intersection C is comprised of 3 elements, 4, 6, and 8, and therefore it has got a chance of 3 in 10. Good. Now we've got the target event, the ancillary events of interest, and now we need to compute further events which reside in the intersection between the target event A and the various ancillary events, A intersection B, A intersection C, A intersection D, and A intersected with the event B intersection C. But again, intersection is an associative operator. The order of operation does not matter. We simply write it down as A intersection B intersection C. And now we have 4 more sets and their associated probabilities. We're now all ready and equipped to write down various conditional probabilities. So let's start by writing down the first, the probability of A given B. Then the probability of A given C, the probability of A given D, and the probability of A given the occurrence of the event B intersection C. Okay, at this point, there's nothing very deep about these manipulations. It's purely arithmetic, and whatever numbers turn out, turn out. At this point, we have just churned through the definition mill, if you will, and provided numerical answers. But we should pause, stop, take a look at these answers and see whether they cast any light upon the situation, whether they tell us something more about what our formal definition is doing. And when we look at these particular numerical answers, we notice something interesting. We start with the unvarnished probability of A being 1 and 2. We discover that conditioned on the occurrence of B, the chance of A has not changed. B, apparently, is not altering the chance of A. It is still 1 and 2. But conditioned on D, the chance of A has decreased. In fact, it's 0 now. Whereas conditioned on C, the chance of A has increased to 3 and 5. Very interesting. What about conditioning on B intersection C? Remarkably, perhaps, the chance of A has now increased even further to 2 and 3. Oh, that is very interesting. This is a political age, and we need slogans to encapsulate such an age. And so here's a slogan for us, a salutary observation that is always worth keeping in mind. Our definition of conditional probability is very, very simple. It's a ratio of an intersection probability to an unvarnished probability. But conditional probabilities can affect native unvarnished probabilities in unanticipated ways.